We ended last class period talking about the Biot-Savart law. And so the Biot-Savart law, if we, just to remind ourselves what we have from electricity, things that are going to be on the test today, we have Coulomb's law, and we have Gauss's law. And how do you decide which one you're going to use?
Symmetry.
Symmetry. Okay, so for magnetism, we have Gauss's law, and we have Ampere's law, and Biot-Savart law. That's 3 laws.
Yes. We can count.
Yes, you can. What's the first thing we do when we talk about, what's a good way to find the magnetic field?
I'm going to guess symmetry again.
Well, that was going to be the answer to my second question.
Oh, well then.
The first question is, what's the first thing? We say, well, Gauss's law doesn't help us. Since we always have magnetic dipoles, we never have a magnetic monopole.
Right.
The net magnetic charge is always 0. And so you just have a 0 equals 0 equation. It doesn't help.
Other than that, I guess that makes sense.
Now we will see next lecture how we can use that law.
Mm-hmm.
But for finding magnetic fields, it's not generally our go-to method.
Right.
So then we have the other two, and then how do we decide between them? And you said symmetry. So the Ampere's law, okay, let me just say Ampere's law, stop sounding foolish. Ampere's law,
like a snobby rich guy.
because that's exactly who I am. Ampere's law is useful if you have a nice symmetry. It can still be done without a nice symmetry, just like you could use Coulomb's law without a nice symmetry, but it's harder. So, our example for finding the magnetic field due to a wire of infinite length, it was easier using Gauss's law than Coulomb's law, but we found it both ways. We did the work both ways.
Oh yeah, we did.
Now, we're going to have the same type of thing going on with magnetism. We could do it both ways, but we want to choose the easiest one. So if you have an exponential symmetry, the Ampere's law is almost always the way to go. If you don't, well, then it's usually going to be the Biot-Savart. So the Biot-Savart law is very literally how you calculate the magnetic field contribution from each little piece of moving charge. So that equation dB means the infinitesimal amount of magnetic field produced by the current in region ds. So that little magnetic field is this, and then of course you have to add, just like before, you like to break dB into components and add the components separately.
Right. So
we're going to go through and do some calculations like that. We're not going to do a case as shown here. We're not going to do a bendy wire that's got some random funky equation to describe its path. We're going to do simple, easy to do geometries.
Okay, here's a quick question.
Go ahead.
When do you use this stuff? Because I can't think of an application where you're calculating this Biot-Savart law for like a generic thing.
Okay.
Sure, electrical engineers probably use it, but I don't know what. But I don't think of them like.
There are some simple things, like let's say a Helmholtz coil. You don't know what a Helmholtz coil is, right?
No.
But have you had an MRI?
Yes.
Okay, in the MRI, you're in this machine that makes a really strong magnetic field, right? You can't have metal in your pocket, it's going to be ripped away. How do they make that magnetic field? With a Helmholtz coil.
Okay.
So what is a Helmholtz coil? It's a coil up here and a coil down here with the separation just so. How do you know what the strength is inside of that Helmholtz coil? Yeah.
Okay. Basically high quality machinery like MRI.
Well, things where you're trying to know and manipulate magnetic fields.
Okay.
This gives you the theoretical how it should work. And so we're going to do equivalent. Now, for an infinitely long solenoid, then we could use Ampere's law, which is what we did. That was the last thing we did last class period.
Right.
But for that Helmholtz coil, you don't have that infinitely long thing. The symmetry is broken. And so then you would be stuck with, well, let's do it with the Biot-Savart law.
Right.
So, and something I thought of as you were talking about it, in the Nathan took the electric circuits class last semester. And one of the things that you pretend doesn't exist is things like capacitance between wires on a circuit board and the interaction of the signal going through this wire and the signal going through this wire. Those are real things. And so when people are designing chips, they have to think about these things. And so that would be another place where, well, you may not use the PHYS law, but where you're going to be using some pretty significant calculations to try to figure out how these things are going to relate. Okay. And of course, rubber meets the road. You learn certain rules like, well, if I have two wires that have to cross, they're not going to cross close to parallel. They're going to cross perpendicular because then the electromagnetic waves have the minimum interaction. That was, okay, let's just do a problem. Suppose a circle. So this is a circle. Is there symmetry in a circle?
Yes.
Yes, there is. Is there an exploitable symmetry for this circle? No. There's not an exploitable symmetry because we can't make a loop that's going to have everywhere the magnetic field parallel or perpendicular to the sides. We don't have, it's going to be constant magnetic field in this region. We just don't have the situations that make Ampere's law very minimal. So that means we're going to have to go with the Biot-Savart law. So if we want to find the magnetic field created by a single loop of wire, so take this example here. Here I ran it as a straight wire, but if I ran as a single loop of wire and I turn the current on, yeah, it moved.
Okay.
What we worry about is the magnetic field on the inside. Right. That's usually what we worry about. Now with this, you could calculate the magnetic field anywhere. And our methods would work, but I'm going to choose the symmetry axis still to make my life simpler. If you go off axis, it's going to be a lot harder. Why is the symmetry axis going to make life easier? Right, the symmetry axis is the one, OX is the symmetry axis.
OX is the symmetry axis?
Or OP, I guess, to get the x-axis there.
Okay.
Why is it going to make life easier to find the magnetic field on that axis somewhere?
Isn't it because the circle is equidistant from that line?
Okay, that's one thing. The circle is
the circle up and down the line.
The circle is equidistant from a point on the line.
Yeah,
that's one.
As for the other, I have no clue.
The other is direction. For any piece that's here, you have a piece in the outside circle that is going to make any magnetic field that is not along the x-axis add to zero. Okay. So we only really need to worry about the x component. We don't have to worry about the y component because we know by symmetry it has to be zero. Now, you and me, we're going to calculate that y component to verify that it's zero.
Right.
But in general, you don't have to because you can make that argument based on symmetry. The y component has to be zero. Or the perpendicular, as it's called here, dB perpendicular, because, well, it could be in the y or z directions, right? You have y is here, z is there. So let's look at what the problem is asking us to do and get to work. So the problem says, suppose we have a current I that's going in this loop in the direction shown. And we're asked to find, it's going, okay, so this is coming out toward us, going down. So this is on the side towards us, that's on the side away. Okay. So if you were to look down at it from point P, it would be going counterclockwise. Okay. And then we're going to find the magnetic field at some point P, a distance x away from the center of the circle along that symmetry axis. So that's our job.
So we're looking for the magnetic field at point P.
Yep.
Okay.
So first things first, we have that equation dB is equal to blah or blah. The difference in the top one and the bottom one is r hat over r squared or r vector over r cubed. The outcomes are exactly the same. So let me start with asking you, which do you prefer to use? This one or this one? We can do it either way. I'm pretty comfortable. I'm not going to make a mistake.
What's the significant difference?
Because here's the difference. If you use the lower one, then your r vector is going to have a magnitude r and a direction.
Okay.
And then that magnitude r is going to cancel with one of the r's down below. If you use the upper one, you don't have any canceling to worry about. But in a different situation where r is changing, you might find that it's better to do the lower one. Right? So it depends on your situation, which one ultimately is the best choice.
Okay.
And right now, there really is no great choice.
Okay, well then let's do the bottom one then, just so I can kind of understand what's going on there.
Okay, so we're going to do the bottom form of the equation here. And so the first thing I'm going to do is to say, okay, what is the magnitude and direction of this dB vector? So first thing we're going to do, first thing we're going to do is the right-hand rule to find the direction.
I think it's down.
So for a piece on the top, right, we're taking a little ds is the piece on top here.
Okay.
And so we have ds vector. What direction is s? Is ds? On this picture, what direction is ds?
Towards P.
The current. ds is going to be the direction of the piece of wire parallel to the current.
Well, then it's going out.
So it's in
going
the
out
z
towards
direction,
P.
which is, yes, out is the correct answer.
Okay. I thought we were pointing towards the P, but
That is what r vector is.
that's what. Oh, we're looking for ds vector.
Yeah, we have ds vector and an r vector.
Okay.
And so ds vector is pointing out, and then r vector is pointing down. Well, just straight down. I forgot.
Oh, it's
R vector is down into to our left. It's like this.
Right.
So I have my hand goes like this,
Okay, so
and the thumb points in this direction.
dB.
So
Okay,
yeah,
that makes sense.
so that's how we get the dB vector. Now in this picture, this is supposed to be a bold B here, but of course I'm putting a vector sign on because who could tell that's bold versus non-bold in a picture that small? Okay, so there's our dB vector, and then we need to break it into components. And so how much of this is in the x direction? Well, we defined this angle theta. How does this angle theta relate to this part of the triangle?
Isn't that the angle between capital R and lowercase r?
Yes. It's important to be able to make that identification, because if you choose the angle definition wrong, of course your answer is going to be wrong. So that's what theta is. So based on that theta, what is dBx? Oops, can't write it there. There's another.
dBx is going to be sine theta.
Adjacent side.
Oh, never mind that. It's going to be cosine. dB cosine.
So the magnitude of dB times cosine theta. And dB perpendicular, what will that be? Magnitude of dB times.
Sine.
Okay, so
Wait, why is it dB perpendicular instead of dBy?
because it's going to go around in a circle, and so it's going to be in the YZ plane.
Oh, okay, but it's always perpendicular.
Yeah, so we're putting perpendicular, so we're just getting the component in the YZ plane.
Okay.
It's an important thing to make sure you got clear. All right, so we have that. Now, what's the magnitude of dB?
Isn't it just the sum of those? No.
Well, that would be true, but I'm looking at from the blue equation,
Oh, it's
right? Because that's what I'm plugging into each of those.
the magnitude is just IDS, isn't it?
Well, we have mu naught over 4 pi r cubed, and then we have, let's not forget the I, because I've done that before. And then we have ds cross r. So ds cross r has a magnitude of dsr times sine, and I'll put phi because it's a different angle, the angle between now ds and r. So what's the angle between the ds? This picture shows dl instead of ds.
Oh,
So that means,
explains why I was confused.
so what's the angle between ds and r?
Lowercase or uppercase?
Lowercase r.
Well, I guess where there's 9 degrees from both.
That's right. It's 9 degrees. So what's the sign of 9 degrees?
0, down 1. Yeah, 1.
I'm putting that r in parentheses so we realize that that's a multiplication there. And so that's just equal to r ds. And so that's what goes here. And now you see that it makes no difference if we chose the upper one or the lower one because we're going to have, that cancels with one of them.
Yep.
And so it's mu naught I over 4 pi r squared ds. And all of this stuff is going to be constant because based on our symmetry, r is going to remain constant.
Yeah.
And so we just have now a line integral ds, which is, yes. So now if we do b in the x direction, that's equal to mu naught, and let me just so I don't make a mistake. Okay, I'm starting at 0. If I go around the circle, where am I going to end with ds? 2 pi r.
Right. Okay.
But we can't forget, whoops.
I was thinking just
We can't forget the cosine theta, though.
that makes sense.
Okay, so we're going from 0 to 2 pi r. If we integrate ds from 0 to 2 pi r, as you said, that gives you s, which is 2 pi r.
Right.
And so if we put this all together,
That's going to be mu naught I over 2 r.
oops.
Wait, hold on. I think there'd be a 2 in the denominator.
Yes,
Okay.
forgot it. All right, so what's cosine theta?
Not theta. I don't know what theta is.
Oh, we drew a picture.
We did draw it. We didn't identify.
Here's theta. So what's cosine theta? By definition, cosine theta is blank over blank.
What, capital R over lowercase.
Okay, so cosine theta is equal to capital R over lowercase r.
That's only in the x direction. So now we need to do it in perpendicular direction.
That's only in the x direction, right? My problem, or my answer, has what might look, wait a minute, over r? Yes, because r changes with distance. R is not the total radius. So this here is going to work for any radius, and remember, r is the square root of r squared plus x squared. So to get my real answer, bx vector, oh, I didn't put directions here. Oh, yeah, I don't have to because it's still the bx component. So the bx component, yeah. So this gives us the magnetic field in the x direction as a function of our x, as long as we stay on that symmetry axis. Now let's check simple results. What is the x component of the magnetic field in the center of the circle? In the center of the circle, what is x? 0. So at the center of the circle, that's mu naught I r over 2 square root of r squared is r. Cancel those r's. Mu naught I over 2. So that's the magnetic field at the center of a loop carrying current I. and having radius r. Where's r in my equation now? It's not. It doesn't matter apparently. So that's the magnetic field in the center.
Hold on. What about the perpendicular?
Okay, so yes, we haven't done B perpendicular. That's why I have a second page.
Oh, okay.
Okay, so we have the x pretty much squared away. We got any position. If x approaches infinity, of course, it's going to 0 because your bottom is going to approach infinity as x approaches infinity. So we have the magnetic field at the center, and then we have the equation if we go away from center. Bueno. And as you just point out, what about the perpendicular part? We know what the answer is going to be. It's going to be 0, but we want to show that that's correct. So we have by is equal to b perpendicular times, let's just define a new angle that I'll call it alpha. We'll do an angle alpha that starts at the y-axis and goes like this. Okay? And so the by is going to be b perpendicular times cosine of alpha, and the bz is b perpendicular sine of alpha. Okay, that's all straightforward. And so I can put in my b perpendicular equation from here, db sine theta, where db is this stuff. So that's equal to over 4 pi well,
Oh, that's the magnitude.
so that's the dB, and then we have sine theta cosine alpha, and this would be
Same thing.
so we have ds and we have the angle alpha, two variables.
Yep.
You need to combine them, but this is actually easy because ds is the arc, a piece of arc, right? And the relationship between angle and arc. No. ds is equal to r d alpha. That's the relationship. So if you integrate ds,
R is radius?
yeah, r is radius. So you get 2 pi r as the circumference from that, right? And so we can just substitute that in. So we have, yeah, I have room. I'm just going to put all of this stuff in brackets. Well, I better write it once. That times, oh, I forgot the R. That capital R is this capital R here. So I changed ds to r d alpha.
Yep.
And then everything that was constant, I put inside the bracket. So this was constant, the r is constant, and all of this is constant. So that's inside the bracket. And then I have to integrate this from 0 to 2 pi. This one here is going to have that same bracket, sine alpha d alpha. So what's the integral of cosine alpha d alpha from 0 to 2 pi?
That's going to be sine alpha is the integral, and then sine of 2 pi is 0. 0.
Okay, so that's 0.
And sine of sine alpha is going to be negative cosine alpha.
What?
Cosine of 2 pi is 1. That's going to be negative 1. minus another negative one, which is a plus one, which is also zero.
Which is also 0. So what we found here is that
Both of those are constant times 0, which is 0.
By equals Bz equals 0. Right, so the B perpendicular, that was changing as we go around. We had break-ins of By and Bz. But now we've done the whole thing. So now with my leading, hopefully that wasn't that difficult.
No.
With your leading, it's going to be harder, right?
Yes.
But what we did was fundamentally the same process that we did when we used, when we used Gauss's law. First we found what dB was, just like we found what dB was. Then we broke it into components. Then we integrated components separately. And we had our answer. So the process is fundamentally the same. The application, not so fundamentally the same.
Right.
Any questions before I move to problem 2?
What was the final answer?
So what was the final answer? The final answer was the bottom one was finding at the center from the top one. So the top one, the blue equation in the box, is fundamentally the final answer. We have that, and then of course, By equals Bz equals 0. Right, that's the complete final answer now.
So we're looking for the magnetic field where again?
At point P.
Okay, so to actually solve the magnetic field at point P, instead of saying x is 0, we would say x is P.
X is whatever this x is, right? It shows x as the variable there.
Right.
So x is however far we are from the sun.
Which is point P.
Well, okay, this is just semantics. Point P is a point, it's not a distance. It's semantics, right? I know what you mean.
Then, all right, I think we're good.
All right. So let's go to another situation, shall we? Look, I didn't even use that. Application to a wire. We did Ampere's law for a wire.
Yes.
What did we do with, just go through the steps of how we applied Ampere's law to a wire. Ampere's law has an additional step. We have to choose a symmetry shape, right?
Yes.
What symmetry shape did we choose?
I think we chose a cylinder? No.
Cylinder would have been for Gauss's law.
Right. So this was probably the worst.
This is a line rather than a closed shape. Like with Gauss's law, it was dA over a closed area. Mm-hmm. With Ampere's law, it's a ds over a closed loop. So what loop shape matches the symmetry of a wire? A circle. So we made a circle with radius capital R that was concentric with the wire, going around the wire. And then because magnetic fields have to do loops, with our cylindrical symmetry, the only shape that you can have in magnetic fields is doing circles. So then we said, aha, along the edge, we have the B is always parallel to the direction it's traveling. It's always constant because B can only change as we get closer or farther, not to go around the circle. And so based on those symmetry arguments, our integral of what we call the circulation, the integral of B ds, what do you want to call it? The integral of B ds is just B times integral of B times ds. B constant comes out as B times integral of ds. Integral of ds is the circumference, so it's B times 2 pi r. So we got that circulation without having to actually do the calculation. And then we said, okay, now we set that equal to mu naught times the current that's passing through it. Current passing through it is I, so that's equal to mu naught I, divided by the 2 pi r, and you have magnetic field. So that's how we found it before. So, I mean, the first time you do it, it's hard. But here I could just verbally work it out. I almost feel like Stephen Hawking. I can do this problem without having to write anything down. And we found B mu naught I over 2 pi capital R. Looks very similar to the equation we had for the magnetic field, the center of a circle, except for the pi.
Yep.
Of course, it's nothing like a circle when it's a straight wire going on forever, but hey. So now let's do it with the Biot-Savart law. So at the Biot-Savart law, we start by saying, okay, we don't have to worry about a symmetry now because we're just integrating along the line. So we have, they're two separate equations. Now the R vector is changing, right? Now the R vector isn't going to be constant.
Right.
So first, let's find the magnitude of dB and the direction of dB. So the magnitude of dB is equal to, obviously we have mu naught I over 4 pi R squared. I'm using the upper one now. And what is ds cross dr going to be? Or cross R going to be? RDS times sine of what?
Theta.
Where theta is the angle between the R vector and the ds vector, which conveniently is what theta is in this picture.
What is the ds vector? Because it kind of looks like kind of a swirly, strange.
Okay, so what is the ds vector? It's important that we have this. Ds means a little piece of the wire.
Yeah.
So it has a height ds. The vector is the direction the current is going, so that's what gives it the directionality.
Okay, so why does it look like it's curling around behind the wire?
It should not. ds, usually we write ds something like this to say it's, that length. The reason it's drawn here with the arrows because it has a direction. And so it's a little piece of vertical pointing up length. So it looks a little different. I don't know, maybe the picture's just not clear enough, but it's just a green upward arrow. The stuff around it is the wire.
Okay.
It's not part of the ds.
Because that kind of looks like they're identifying ds as something weird.
Right, it's just the vertical arrow is the ds.
Right.
And the yellow stuff is not part of it. So it's important, that you identify the angle here is the angle between ds and the R vector, which they already identified the correct angle, right? If you had put, something else, well, it's actually hard to go wrong, but because it's sine, you could have put this one here and you would have had the same outcome. And that's why I said it's hard to go wrong if you use this angle or this angle. This one's the same as theta, and this one here is its complement, but you would have had the same, or excuse me, not complement, it's supplement. It would have worked out either way. So let's move on then. dB magnitude is that times, and I did the top one, so it was R hat. If it's R hat, then there's no R here. And so it's sine theta ds. Okay, so that's our dB magnitude. Now we need to break into components. What direction, just using this picture here, what direction is dB pointing? And I know it has a picture, you can figure out the picture, but I want to use the right hand rule. So what finger is first? Index finger is which one?
I think it's ds.
Yes, right. So ds is pointing up. So with your index finger pointing up, what direction do your middle fingers to go?
On vector.
Okay, so like this.
So it's going in.
So it's going in. So that's what it has shown here, going in. So at this location, it's just going in. So my B in, it's all in one direction. So I'm just doing B in. Now, it seems like this is good, but what's the problem with this integral as it sits?
You have a lot of constants and stuff.
Oh, that's not a problem. Look, I can fix your problem. Now I don't have a bunch of constants inside.
Well, you're integrating with respect to s, but you've got theta.
Right, I got two variables, so I have to combine them. So how do I combine these?
Trigonometry.
That sounds good. That sounds good. Oh, I put r outside. That's a problem too, because r is now a variable. I have three variables. Not us. Not us. So let's see what we can do here. Oh, I know. We can do exactly what we did before when we did the line integral with Coulomb's law. So we can say, well, let's see now. Cosine of theta is equal to, and a little bit problematic here. I said this is theta, but this isn't theta at all, is it?
No.
Let us pretend that we were down here so I can do my work easier. I would have then this angle here would be theta. This distance here would be minus s.
Okay.
Right, so this way I can do it without messing up, I hope.
Yes.
So cosine theta is the adjacent side, r, over the hypotenuse, lowercase r. Okay, that's actually not so hard, right?
Yeah.
Tangent theta.
Wait, hold on. Isn't cosine theta actually s over r?
Cosine is adjacent side, yes. Cosine theta would be minus s because that side's minus s.
Sorry, sine theta would be capital R. And then tangent theta is capital R over negative.
Yeah. Yeah, there we go. And I hope this minus s thing is going to work out right for me. I think it will, but there could be a minus sign error in my answer. Just be aware that I'm not 100% confident about my sign choices. So we have a sine theta in there, and we have a ds. How do I get ds? Well, this is not as easy as before, is it? It's not as easy as before because this, if I took the derivative of this, it wouldn't turn out very well for me. And this here has all three variables in it. This one here only has two, but it doesn't have s. So I'm just going to boldly go, take the derivative of this one again. And there I have a relationship between s and d theta and theta. And then recognizing that cosine theta is minus s over r, then 1 over cosine squared theta is equal to r squared over s squared. And so r squared d theta over s squared equals capital R ds over s squared. Now I can cancel these s squareds, and I have r ds is equal to lowercase r squared d theta. That wasn't so simple. So I can replace ds. I'm going to change color here. ds is equal to r squared over capital R d theta. And if I put that in, now life got easier.
Yeah.
Because these r squareds cancel. This r is a constant. And so my Bn equals mu naught I over 4 pi capital R integral of sine theta, or yeah, d theta from, and what does my angle start at? It's going to start at 0. If we keep going down to infinity, that angle is going to pinch down to 0.
Yep.
And if we go to maximum, it's going to go to pi.
Yep.
Yeah, if we go up to an infinity, it'll go to pi. You're not looking. Right, because this will flatten out 180 degrees.
Yeah.
And so now we just have to do this integral.
That's going to be negative cosine theta minus the plus cosine theta. It's going to be 1 plus 1, which is 0. Negative 1.
No. Negative a negative 1. This negative is there. And you from the words you spoke, you'd gone through that in your head the first time.
Yeah.
So that's my B inside, or B in, not in, but the direction it's going is in the inward direction. So it's going in that direction of the x, going away from us, with the magnitude of mu naught I over 2 pi r. This was harder, right?
Yes.
Yes, it was harder, but just like before, we showed that we can do it both ways. So, if in doubt, you can do it both ways. This one might be a lot easier than the other. All right, that is my preparation for the day using Biot-Savart law. Haben Sie eine Frage?
7 questions?
Yes. Ja, jawohl.
Can't think of them now.
Then wir sind out of here.